In this video, we're going to discuss about Euclidean domain, and basically what we're going to do is we're going to define a Euclidean domain, and then we're going to prove one of the three basic properties of a Euclidean domain. Okay, alright. First of all, to define a Euclidean domain, we're going to need an integral domain. Okay, we're going to need an integral domain. So by integral domain, we mean a commutative ring. Having no zero divisors. Okay, having no zero divisors. Right. Now, together with this integral domain, we'll also need a function from the set of non-zero elements of E to the set of non-negative integers satisfying the following properties. Okay, following properties. The first property is that for every non-zero elements x and y in E, we have this inequality for xy belonging to E minus 0E. Okay, first condition. Second condition is that for every non-zero elements A and B of E, we can find two elements of E, Q and R, such that A is equal to BQ plus R, okay, where either R is equal to 0, and if R is not equal to 0, then we have dr to be less than dB. Okay, these two conditions. So we have an integral domain and we have a function d satisfying these two conditions. Then we say that the integral domain E together with the function d is said to form a Euclidean domain. Okay, this is the definition of the Euclidean domain. An integral domain together with this function d, which we shall now refer to as the d-value function. Okay, d-value function is said to be an integral domain together with the d-value function is said to be a Euclidean domain. Now, if x is any non-zero element of E, then we say that dx is the d-value of x. Okay, and obviously since 0 is not in the domain of d, d0 is undefined. We do not define d0 at all. Okay, we do not even extend this function d to include the point 0. All right. Okay, and yeah, the second condition right here, this second condition is often called the division algorithm because this condition resembles the well-established division algorithm from number theory. Alright, this is the definition of the Euclidean domain. Now let's look at the first property of the Euclidean domain. Okay, now if we have a Euclidean domain and I is any ideal of the Euclidean domain, then we shall have this representation for I. Okay, we can find some a0 in I such that I can be written as the set a0 times x, where x runs over E. Alright, now to prove this, let us assume that the given conditions hold. Okay, the given conditions hold. Then we can have the following two cases. Okay, since I is an ideal, it is possible that I is the zero ideal. Okay, I is the zero ideal. Now in this case, we can say that there exists a0 belonging to I, where now if we are supposed to take any element from I, if I is a zero ideal, then that element should be the zero element. Okay, the zero of the ideal, or the zero of the Euclidean ring. Alright, such that I is equal to the zero element is equal to a0x, such that x belongs to E. Okay, and therefore for this case the proof is complete. Now why does this work? We know that for any ring R, okay, for any ring R, we have 0R times x equals to x times 0R equal to 0R. Alright, so if we allow x to vary over, if we are allowing x to vary over E, then each and every time a0x gives us 0E, since a0 is 0E. Okay, as per this condition, as per this property. Alright, this completes the proof in the first case. So let's move on to the second case, where I is not the zero ideal. Okay, now if I is not the zero ideal, then since an ideal is necessarily a subring, it cannot be an empty set. I is non-empty, and I will contain the zero element, but not just the zero element. Alright, and therefore I has some non-zero elements of E as well. Okay, in this case I has some non-zero elements of E as well. Some non-zero elements of E as well. So I minus the zero element is a non-empty set, and dx, the d value of x, is defined for every x belonging to I minus the zero element. Okay, since x is a non-zero element of I, it is obviously a non-zero element of E, and for non-zero element of E, for any non-zero element of E, by definition of a Euclidean ring, the d value is well defined, and therefore since this is non-empty, and this is well defined, we can say that this set, the set of d values, of non-zero elements of I is a non-empty subset, because there are x's in this set, okay, I minus the 0e, and for such x's dx actually exists. Therefore this is a non-empty subset of the set of whole numbers, or the set of non-negative integers, because now where do we get this from? We get this from the definition of the d-value function, because its codomain is the set of non-negative integers. Alright, so now as per the Weyl ordering property, we can conclude that the minimum of dx such that x belongs to I minus the 0 element exists. Okay, this minimum of elements, the minimum element of this set exists. So let us take k to be equal to minimum of these d values. Okay, x belongs to I minus the 0 element. Now by definition of a minimum, what happens is that by definition of a minimum, what do we get is that, okay, where's my cursor? Right. By the definition of a minimum, what can we conclude is that k is less or equal to dx for all x belonging to I less than 0 I minus the 0 element, and k belongs to the set of which it is the minimum. Alright, of which it is the minimum, like this. Now let's call this 1, and let's call this 2. Okay, now from 2, as per the definition of this set, since k is in this set, we can say that there exists some a0 belonging to I minus the 0 element, okay, such that k is equal to d of a0. Alright, this is what we can say. Let's call it condition 3. Now from 3 and 1, we have, what do we have? dA0 to be less or equal to dx for all x belonging to the set of non-zero elements of the ideal I. Okay, let's call this statement 4. Alright, The statement 4 is going to be a crucial part of this proof, as we shall see. Okay, this is it. Now what are we going to, now what we want to do is we want to show, okay, we want to show that I is equal to a0x, x belongs to E, okay, where this a0 is obtained from statement 4, or you can say from statement 3. The same a0 we have obtained from statement 3, or you can say statement 4. Okay, alright. Now to show that two sets are equal, first of all we are going to show that this set is a subset of the ideal I. Okay, now to prove this, what are we going to do? We're going to take any element Z in the set like this, be arbitrary. Okay, now let's take this to be arbitrary. Then as per the definition of this set, we can say that Z can be written in the form of a0 times x0, where, okay, not where, for some, not every x, but for some x0 belonging to E, because every element of this set should have this form. Okay, for some x0 belonging to E. So we can say that Z belongs to I. Why? Because a0 already was a non-zero element of I, so it is essentially or necessarily an element of I. Okay, and x0 is some element of E. Now as per the definition of a definition of an ideal, if R is the ring and X is the ideal being considered, then we have Rx in I as well as XR in I. Okay, using this condition we can say that now we have a0 in I, okay, instead of this we have a0, and instead of R we have x0. So a0 x0 should be in I because I is an ideal. Since a0 x0 is equal to Z, and as a0 x0 belongs to I, we can say that Z belongs to I. So what follows is that a0x, x belonging to E, is a subset of I. Okay, let's call it equation statement 5. Alright, now what are we going to do is that we're going to show the converse, a0x, such that x belongs to E. Okay, this one. Now for this we're going to take an arbitrary element in the ideal I. Okay, then we can have two cases. If Z is equal to the 0 element, then what do we have? Z can be written as a0 times the a0 times 0e, and so Z is in the set a0x where x belongs to E. Okay, why is this? Because what we can do is that Z is equal to 0. Okay, Z is equal to 0. We already have Z is equal to 0. So since Since 0 can be written as the product of 0 and any element of E, okay, any element of E, and in particular an element of I, because I is a subset of E, this expression holds. So Z is equal to A0 times some element of E. Sorry, some element of E. So this is in the form of A0x. Okay, 0 is in the form of A0x. 0 is equal to A0 times A0 times the 0 element. Okay, that's why if Z is equal to 0E, then Z is in the given set. Okay, first case is complete. Now if Z is a non-zero element, then we can use the division algorithm. By using the division algorithm, what can we get? We can get QR belonging to E such that now let's see, in this case Z is not equal to 0, and since A0 is in the set of non-zero elements of I, A0 is also not equal to 0. Since I is a subset of the Euclidean domain, we can easily use the division algorithm. Okay, and as per the division algorithm, what can we get? Z to be equal to A0 times Q plus R. Now if you look at the definition, let's look at the definition. Okay, I'm taking A to be Z and B to be A0. Okay, all right. Now let's carry on with the proof. And in this condition, as per the division algorithm, R can be either 0 element, and if R is not equal to 0, then dr should be less than dA0. Okay, dA0. Alright, now what are we going to do is that we're going to claim that this holds. We're going to claim that R is equal to 0E. Now if possible, let our claim be wrong. Then this means we are assuming that R is not equal to 0E. Then what are we going to get? dr to be less than dA0. Okay, dr to be less than dA0, and let's call it statement 6. And furthermore, since Z is equal to A0 Q plus R, also R equals Z minus A0 Q. Now this will belong to I. Okay, this will belong to I. Why? Because Z was already an element of I. Okay, A0 was an element of I, non-zero element of I. This was a non-zero element of I. Q was an element of E. So by the definition of an ideal, A0Q is also an element of I. Now by the definition of an ideal, if we have xy in the ideal, we're going to get x minus y in the ideal. Okay, so since Z is in the ideal, A0Q is in the ideal, Z minus A0Q is in the ideal, and therefore since z minus a0q is equal to R, we can say that R is in the ideal I. Okay, so let's see, from here we have R belongs to I, and we're assuming that R is not equal to 0. So these two statements allow us to conclude that thus R is a non-zero element of I. Okay, R is a non-zero element of I. That's what we can conclude. Now, since R is a non-zero element of I, since R is a non-zero element of I, from statement 4, this statement right here, from statement 4, we can say that dA0 is less or equal to dr. Okay, d0 is less or equal to dr, because since we have dA0 to be less or equal to dx for all x belonging to the the set of non-zero elements of I, and since R belongs to this set right here, particularly we can write dA0 to be less or equal to dr. Okay, using statement 4. Now, okay, so from 4 we have dA to be less or equal to dr, dA0, sorry. Okay, let's call it statement 7. Let's call it statement 7. Now let's compare statements 6 and 7. If we compare statements 6 and 7, then what can we say? That here statements 6 and 7 give us a contradiction, and we have obtained this contradiction after assuming that our claim is false. Okay, after assuming that our claim is false. So 6 and 7 gives us a contradiction, and since we have obtained this contradiction by assuming that our claim is false, this assumption right here, we conclude that this is actually false and this is actually true. Okay, so what can we say is that thus we have claimed the right thing. Consequently, Z will be equal to A0Q plus R is equal to A0Q plus 0E is equal to A0Q. Now, since Q is an element of E, Z is in the form of A0 times an element of E. Okay, so Z is in the set A0X such that X belongs to E, because Z is in this form. Okay, because Z is in this form. Alright, since Z in the beginning, now in both the cases, if Z is equal to 0, then also Z belongs to this set, and if Z is not equal to 0, still Z belongs to this set. Therefore, we can say that if Z is any element of I, then Z should be in this set, okay, whether it's 0 or non-zero. Thus, we've taken any arbitrary element of I and we have shown that the same element is in this set. Okay, the same element is in this set. Thus we have this statement to be true. Now from 5, I guess it was 5 and 8, we conclude that I is equal to a0x such that x belongs to E, where a0 is some element of I. That is, there exists some a0 belonging to I such that I is equal to a0x, x belongs to E. This is what we were supposed to do. Alright? Okay. This is what we were supposed to do, and yeah, that's all for this video. And in the next video we're going to show that every Euclidean domain has a unit element or a multiplicative identity. Alright? Okay. Thank you very much.